A pilot initiates a missed approach. The airplane suddenly rolls and impacts the ground in a 17-degree, nose-down pitch attitude. An airplane on approach experiences pitch excursions of greater than 70 degrees. The airplane does not recover. An airplane is on an automatic ILS approach, but an error has been made with the autoflight system. The airplane enters a severe nose-high pitch attitude, stalls, and does not recover. Three different accidents, three different causes, but one common thread. At some point in each case, the airplane was upset and entered an unusual attitude. That is, the plane unintentionally exceeded the parameters that you, the pilot, normally experience in day-to-day operations. Every day around the world, tens of thousands of airplanes take flight. As you well know, an overwhelming majority of those flights proceed without incident. Airplane upsets are not a common occurrence. However, there have been many loss-of-control incidents in multi-engine turbojet airplanes. And since the beginning of the jet age, there have been a significant number of commercial jet transport accidents attributed to control problems. As you'll see, causes for airplane upsets are varied, and in some cases, difficult to agree upon. But one thing everyone agrees with is that once your airplane is upset and enters an unusual attitude, you may have little time to react. The actions you take are critical to recovery. With this in mind, airlines, pilot associations, airplane manufacturers, and government aviation and regulatory agencies feel it is appropriate that you receive airplane upset recovery training. This video will define airplane upset. We'll look at causes, and we'll review aerodynamic principles that form a basis for recovery. There's no doubt, you never want to be in a situation where your airplane has rolled or pitched out of control. But if you do find yourself in such a situation, the information that follows can play a vital part in a successful recovery. An airplane is defined as upset if it unintentionally exceeds the parameters normally experienced in line operations or training. Specific values may vary among airplane models, but the following conditions are generally agreed upon. Unintentional pitch attitude greater than 25 degrees nose up. Unintentional pitch attitude greater than 10 degrees nose down. Unintentional bank angle greater than 45 degrees. Or, even within these parameters, but flying at airspeeds inappropriate for the conditions. The causes of airplane upset are varied, but these can also be broadly categorized. Upsets that are environmentally induced, those caused by airplane components, those caused by human factors, or those induced by a combination of any of these. Interpreting and responding to rapidly changing environmental conditions is a constant way of life for the working pilot. These conditions can also lead to an airplane upset, although not all of them have a direct effect on the airplane itself. For example, a rapid environmental change may dictate a quick transition from VMC to IMC. During this transition, it's often easy to get distracted. Research shows that an upset is more likely to develop when the flight crew is distracted. Environmental conditions can also cause visual illusions, such as false vertical and horizontal cues. During such illusions, instruments can be misinterpreted, and again, the flight crew can be distracted. The biggest danger from environmental conditions, however, are those that directly affect the airplane flight path, such as the various types of turbulence a pilot might encounter. Industry study has validated that wake vortex turbulence can contribute to an airplane upset. Wind shear has also been extensively studied and is a known cause of upset. Mountain waves. Severe turbulence advancing up one side of a mountain and down the other is another environmental factor that can affect the airplane flight path. As is clear air turbulence, often marked by rapid changes in pressure, temperature fluctuations, and dramatic changes in wind direction and velocity. Other environmentally induced factors that can contribute to or cause an airplane upset include thunderstorms and weather conditions that result in ice buildup on the airplane. The best solution to environmental hazards is to avoid them when possible.
Moncton Center, Atlantic 250, requesting 20-degree deviation to the left for weather.
Today's airplanes are remarkably reliable, and malfunction of components or equipment that can lead to an upset are rare. Because of this high level of reliability, when these problems do occur, they can surprise the flight crew. Airplane component problems, such as an instrument failure or an autopilot failure, fall under this category. Again, the result can be direct, such as an autopilot failure resulting in a pitch moment, or there can be an indirect effect, if the flight crew has been significantly distracted by the failure of a particular component. Other causes include flight control anomalies and system failures that lead to unusual control input requirements, as might be experienced with an engine failure, failure of the yaw damper, the spoilers, the flaps or slats, the primary flight controls, or as a result of structural problems. Human factors must also be taken into account when examining possible causes. Cross-check and instrument interpretation is an example. Misinterpretation of instruments or a slow cross-check may lead to an upset.
You're cleared to 3.
Okay, starting down.
An upset can result from unexpected airplane response to power adjustments, automated functions, or control inputs, inappropriate use of automation, or by pilots applying opposing inputs simultaneously.
Hey, check your speed.
The autopilot's not holding airspeed very good.
You're in vertical speed mode.
Okay, I forgot. Go on flight level change, 240.
As previously mentioned, inattention or distraction in the flight deck can lead to an upset. This includes any type of distraction that causes the flight crew to disregard control of the airplane, even momentarily. Spatial disorientation, the inability to correctly orient oneself with respect to the Earth's surface, has been a significant factor in many airplane upsets. Other rare but possible human factors include pilot incapacitation due to a medical problem, or even rarer, a hijacking situation. A combination of any of these factors can also lead to upset. It's important to remember that we're trying to look at all possible causes here, no matter how remote the possibility. The fact is, it's sometimes this very remoteness that allows an upset situation to develop. Now that we've taken a look at the possible causes, let's take a few moments to review some key aerodynamic principles. These are the things you learned at the beginning of your flying career. You now react instinctively on the flight deck and rarely need to think about aerodynamic theory. However, in an airplane upset situation, these principles form the basis for recovery. We've asked the chief test pilots for Boeing and Airbus to assist us in this discussion. These are pilots who have taken their airplanes to the extremes.
When discussing large airplane aerodynamics, 3 words often enter the conversation: Energy, the capacity to do work. Flight path, the actual direction and velocity an airplane follows. And maneuver, a controlled variation of the flight path. In an airplane, the ultimate goal of using energy is to maneuver the airplane to control the flight path. The energy created by the thrust of the engines and the lift generated by the wings is controlled by the thrust levers and flight controls to overcome gravity and aerodynamic drag. In other words, flight controls give you the ability to balance the forces acting on the airplane in order to maneuver, to change the flight path of the airplane. The direction of the lift produced by the wings is independent of the direction of gravity. Two other important principles: energy management and angle of attack. An airplane in flight has two types of energy: kinetic, or airspeed, and potential, or altitude. You exchange speed for altitude and altitude for speed. The angle at which the wing meets the relative wind is called the angle of attack. Angle of attack does not equate to pitch angle. Changing the angle of attack either increases or decreases the amount of lift generated. But beyond the stall, the angle of attack must be reduced to restore lift.
Now let's look at the elements of stability. Movement around the lateral axis of an airplane is called pitch and is usually controlled by the elevator. At any specific combination of airplane configuration, weight, center of gravity, and speed, there will be one elevator position in which all of these forces are balanced. In flight, the two elements most easily changed are speed and elevator position. As the speed changes, the elevator position must be adjusted to balance the aerodynamic forces. For example, as the speed increases, the wing creates more lift. If the airplane is at a balanced in-trim position in flight, it will generally seek to return to the trim position if upset by external forces or momentary pilot input. This is called positive longitudinal static stability. We've all experienced this and are familiar with the requirements to apply pull forces when an airplane is slowed and push forces when an airplane speeds up. Changes in airplane configuration will also affect pitching moment. For example, extending wing-mounted speed brakes generally produces a nose-up pitching moment. Airplanes that have electronic flight control systems, commonly referred to as fly-by-wire, may automatically compensate for these changes in configuration. Thrust affects pitch as well. With underwing engines, reducing thrust creates a nose-down pitching moment. Increasing thrust creates a nose-up pitching moment. Airplanes with fuselage or tail-mounted engines, or those designed with electronic flight controls, produce different effects. Whatever type of plane you are flying, you need to know how the airplane will respond. The combination of elevator and stabilizer position also affects pitch. In normal maneuvering, the pilot displaces the elevator to achieve a change in pitch. The stabilizer is then trimmed by driving it to a new position to balance the forces. This new stabilizer position is faired with the elevator. If the stabilizer and elevator are not faired, one cancels out the other. This condition limits the airplane's ability to overcome other pitching moments from configuration changes or thrust.
Now, let's continue this discussion by taking a look at yaw and roll. Motion about the vertical axis is called yaw and is controlled by the rudder. Movement of the rudder creates a force and a resulting rotation about the vertical axis.
The vertical stabilizer and rudder are sized to meet two objectives: to control asymmetric thrust from an engine failure at the most demanding flight condition, and to generate sufficient side slip for crosswind landings.
To achieve these objectives at takeoff and landing speeds, the vertical stabilizer and rudder must be capable of generating powerful yawing moments and large side slip angles. Motion about the longitudinal axis is called roll. Control inputs cause the ailerons, and then spoilers, to control the airplane's roll rate. The aileron and spoiler movement changes the local angle of attack of the wing, changing the amount of lift, which causes rotation about the longitudinal axis. During an upset, there may be unusually large amounts of aileron input required to recover the airplane. If necessary, this can be assisted by coordinated input of rudder in the direction of the desired roll.
However, when a large transport swept-wing airplane is at a high angle of attack, pilots must be careful when using rudder for assisting lateral control. Excessive rudder can cause excessive side slip, which could lead to departure from controlled flight.
As angle of attack increases, aileron and spoiler effectiveness decrease because the airflow begins to separate over the wing. However, the rudder airflow is not separated. It remains aerodynamically effective.
In some aircraft configurations, there is a certain crossover speed at which full aileron and spoiler deflection is necessary to counter the roll due to full rudder deflection and the resulting side slip. Below this crossover speed, the rolling moment created by ailerons and spoilers is gradually unable to counter the rolling moment induced by the side slip generated by full rudder deflection. The airplane must be unloaded to reduce angle of attack, and the airspeed must be increased to maintain lateral control.
In contrast, very high speeds in excess of VMO and MMO cause control surfaces to be blown down, rendering them less effective.
The main concern at high speed, in excess of VMO and MMO, comes from vibrations and high air loads that may lead to structural damage. Other effects often include reduced effectiveness or even reversal of control response. Any pitching moment due to speed brake extension or retraction is more pronounced at high speed, and pitching effects as a result of thrust changes are less pronounced.
High-speed buffet is caused by shock wave instability. As the airplane exceeds its cruise speed, the shock wave that runs along the wing upper surface becomes strong enough to cause the beginning of a local separation or stall. This causes the flow over the wing to fluctuate, leading to rapid changes in drag and the position of the center of pressure. The ensuing buffet results in a loss of aerodynamic efficiency of the wing, which will impact the high-speed dive recovery. The buffet can be disconcerting and will normally not be symmetrical on each wing, resulting in a rocking motion during a pull-up. The pilot should relax the pull force if high-speed buffet is encountered.
Altitude and Mach also affect the performance of the control surfaces. The higher the altitude and Mach, the more sensitive the airplane is to control surface movements, making the recovery more difficult. Asymmetric thrust affects roll. When there is asymmetric thrust, side slip is created and thus roll. This is normally countered with rudder and lateral control. Obviously then, reducing an asymmetric thrust condition will also reduce the side slip associated with it. The definition of VMCA is the minimum flight speed at which the airplane is controllable with a maximum of 5 degrees bank when the critical engine suddenly becomes inoperative with the remaining engine at takeoff thrust. Below this speed, there is insufficient directional control. As the airspeed decreases, the ability to maneuver the airplane also decreases. During a full or deep stall, the flight controls become less effective because of the high angle of attack. However, the rudder remains effective at lower speeds. This can be good or bad. At speeds above stall, the rudder can assist the airplane's ability to roll. But at slower speeds, there will be a delay after application of the rudder before roll response becomes apparent to you. Also, the amount of rudder used and the rate at which it is applied is critical. The bad part is that at speeds approaching the stall speed, or speeds below the stall speed, use of rudder applied too quickly or held too long may result in loss of lateral and directional control and cause structural damage. At any speed, large aggressive flight control reversals can lead to loads that can exceed structural design limits.
Another consideration for longitudinal control is G-load. That is, the amount of load factor that is aligned with the vertical axis of the aircraft. In a level turn, or pull-up, the wing has to create more lift and the pilot feels more G-load. The increased G-load will also increase the stalling speed. Generally, the elevator and stabilizer have sufficient control authority to drive the wing past its stalling angle of attack, even at high speed, which can adversely affect pitch and roll control. This means that the wing can be stalled. In this case, regardless of the pitch attitude, a pilot cannot command a specific bank angle or flight path even at high airspeeds. The aircraft has entered into an accelerated stall. The wing loading must be reduced to recover from this stall and regain pitch and roll control. Aircraft with electronic flight control systems may provide protection against entering into many upset situations. These systems also assist the aircraft to return to normal flight if necessary. However, when fly-by-wire aircraft operate in the degraded mode, flight control inputs and the responses are similar to non-fly-by-wire aircraft.
The aerodynamic principles we've reviewed are applied to airplane design.
During flight testing, all airplane manufacturers exceed these parameters to help prove the safety of the airplanes you eventually fly. A working knowledge of these principles is vital to a successful recovery from an upset situation.
In this video, we've defined what an airplane upset is. We've looked at causes, and we've reviewed the aerodynamics associated with recovery. We've laid a foundation. To build upon this foundation, follow-on training should review specific recovery techniques.